No cry. Exhale. Donovan Knight. Serena Salazar. Peyton Stallion. Brianna Watson. And then probably yep. Well, I guess I'll get started. So I'll start with some announcements. First homework assignment, which is very straightforward. It's just, this is how you use WebAssign, basically. That will be due on Friday the 23rd. So that's next week, Friday. I just want to give everyone enough time to get signed into WebAssign and get everything working. And the chapter 1 homework will be due on Thursday the 29th. And that's later than most homeworks will be. In general, I tried to set it up so the homeworks are going to be due on the day that you have the quiz. So just so homework and quiz are due on the same day, you can get it done to practice for the quiz. So the chapter 1 quiz will be on Thursday the 22nd. That's next week, Thursday. And it will be in the SI session. So later today, you're going to go to the SI session in room, look this up, 268 at 11:30. And David there will teach the supplementary instruction, and you'll be having your quizzes during the SI session. Any questions about any of this? No, it's next week. First quiz is next week. It'll be after we finish chapter 1. So the quizzes are on each chapter. So after we finish each chapter. So no, there's no quiz this week. First homework due on Friday the 23rd, just to give you a little extra time to get used to it. If you want to get started on the chapter 1 homework, feel free. It's available. Okay. I will continue with, oh, it helps if you turn it on. Let's talk about how we communicate results. So one of the most useful tools we use when presenting results in science are graphs. Line graphs or scatter plots are some of the most common tools used. So two variables are compared. The independent variable gets plotted on the horizontal axis generally, and the dependent variable on the vertical axis. Here we're looking at gas volume versus temperature. What we're trying to understand is how gas volume varies as we control temperature. These points are the individual points we've plotted, and then this line here is sort of a fit. So often graphs are used to communicate information. There'll be some slightly odd plots, but graphs are ways that we can organize data so we as humans can see patterns in them, which is what we're generally looking for when doing science. Sometimes we want to represent how much of certain things there are, so we use things like pie graphs, circular pie graphs. They show a fixed quantity, a total, and as fractions of the whole. So these are Texas weather deaths from 1988 to 2005 and their causes. So we're splitting up the total into the parts, and we this lets us see how much comes from each source. So you can see the biggest source of Texas weather deaths is flooding, followed by extreme heat. And then everything else is much smaller. Now you can also, if you're not looking at how something varies compared to another variable or something, but you're just doing it in categories again, you might use bar graphs. So bar graphs represent quantitative data with bars, but here you can see each of these sections is a category. And each of the colors is a different sort of situation, the weather fatalities for 2013, the 10-year average, and the 30-year average. So this can sort of let you see, comparing 2013 to the 10-year average and the 30-year average lets you look at trends. But these are also in each category. The bar graphs tend to be used when you're splitting things into sort of buckets or groups. You're not like looking at a continuously varying quantity. So when we want to talk about something we've observed or looked at and share it with someone else, we use systems of units to share that information with other people so that they can know exactly what we're talking about. So a measurement is expressed with a magnitude, a quantity, and a unit. So an example would be 25 meters, or I don't know, 10 inches, or 300 pounds. These are all quantity and unit. And most of the units we talk about will be based off of three fundamental quantities: length, mass, and time. They may be combinations of them. So, 15 miles per hour, that's length over time. And a standard unit is a fixed and reproducible value that people have agreed on that we use to take accurate measurements. For example, a meter, this, is defined as the distance traveled by light in 3 times 10 to the minus 9 seconds, roughly. There's a very specific number, which I'll give it a little bit, but it's the distance traveled by light in a very specific period of time. Basically 1/300 millionth of a second. There are two major systems of units in use. There is the British or English system, or sometimes called imperial. Name? What? That's really only used widely in the United States. The official term for this is US customary units, because they're unique to the US, basically. And then the metric system, which is used throughout most of the world. So the British or English system is things like miles, inches, pounds, seconds. The metric system, which is used pretty much everywhere else other than the US, is things like kilometers, meters, grams, etc. And the US has actually officially adopted the metric system in 1893. We just haven't actually started using it. And in fact, at this point, everything in the US customary units of the British or English system is defined in reference to the metric system. A pound is a weight of so many kilograms. And so on. It's all defined based on the metric system. So the US officially adopted the metric system in 1893, but continues to use the British system because politics, lobbying, etc. And people's inability to change. So the first general quantity that gets measured is length. This is the measurement of space in any direction. Space has 3 dimensions. You can do 3 completely independent directions in space. for example, up in, length, width, and height. Those are fully independent. I can describe any location in space with three numbers, basically. So space has three dimensions. The metric standard unit for distance or length is the meter. All the metric units were originally attempted to be defined based on quantities in nature to make it more scientific, because it was a very Enlightenment sort of thing. It happened during one of the French revolutions. I can never remember which one. But so, for example, the meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole. So let's define our units based on nature instead of your foot. And the British standard unit is the foot. It originally referenced a human foot. That's a very old unit. The foot as a unit of measurement has existed for thousands of years. The Romans used the foot, but the size of what it was a foot varied over time, and there was definitely a period where it varied from place to place. So the foot would be different in different regions. So this was originally the meter was originally defined as a quantity of nature, 1/10,000,000th of the distance from the equator to the North Pole. The problem with this, when you start to get really accurate, is that distance varies depending on where you measure it. And so it's sort of tricky. That there were some assumptions made that the Earth was perfectly spherical and things. It's a little bit longer than a yard. It has now been defined based on a fundamental constant of the universe. 1 meter is the distance traveled by light in a vacuum in 299,792,458th of a second. Basically, what we did is we set the speed of light to an exact whole number. We measured it as best we could, and then we rounded it to an exact whole number and used that to define the meter, because we didn't want to actually change our meter much. So the speed of light is exactly 299,792,458 meters per second. So that in 1 second, light will travel 299,792,458 meters, or more accurately, 1 meter is the distance traveled in 1 over that number. The next unit is mass. This is, in fact, of the base units of the metric system, was the most recent to finally be defined based on a constant of the universe. It was originally defined as the mass of a 10-centimeter cube of water. But the problem is the density of water varies with temperature, contaminants, etc. Not the best reference. An object's mass is always constant. This is a kilogram. The reference is a kilogram. And so so mass is a fundamental unit that will remain constant throughout the universe. So if you go to like say the moon, your mass will not change. Your weight will change, because weight is a measure of how hard gravity is pulling you down. So if you go somewhere with weaker gravity, your weight is less, which does mean that one of the most amusing ways to lose a very small amount of weight is to ride an elevator up to the top of a very tall building. Because gravity is ever so slightly weaker because you are further from the center of the Earth. So the metric standard unit for weight is a kilogram. And it was originally defined as the amount of water in a 0.1 meter cube. And up until 2019, so quite recently, it referenced a physical object. The kilogram was this platinum iridium cylinder in a vault in Paris. And the problem was we knew its mass was changing. because we'd made a bunch of copies, and when we brought them all together again, they were not all the same mass. So we knew we had a problem there. So now it's based on a fixed value of Planck's constant, which is a fundamental constant that has to do with how light, the energy of light and things like that. It's another fundamental constant of the universe. And so Planck's constant is now defined to have an exact value of 6.62607015 times 10 to the minus 34 kilogram meters squared per second. And this was done by very accurately measuring Planck's constant using something called a watt balance or a Kibble balance, which basically weighs things in gravity against a very precisely measured electric force. And by balancing that out properly, you could actually measure Planck's constant. And by measuring Planck's constant very accurately, you could use that to define the kilogram. And the process here is kind of insane. Like the start of this, before you install one of these things, you have to measure the strength of gravity throughout the room you're putting in, kind of thing. The metrology was very impressive. So here's an example of one of those platinum iridium cylinders that was the original, and it was the definition up until 2019. This is one from the US. It's at NIST in Washington, D.C. It's ever so slightly smaller than a kilogram. It used to be exactly a kilogram, but now it's 0.999999961 kilograms, or it was, and then because it had been losing mass over time. And this physical object that had been used since the 1800s was replaced by a new definition based on Planck's constant in 2019. That was a big deal because it was the last of the units to not be defined based on some sort of fundamental aspect of the universe. The mass unit for the British system is the slug. Nobody uses it. We use the pound, which is technically a measure of force or weight. It's related to gravitational attraction, but it's also, it's the measure of how much force gravity is applying to you. But all American engineers use mass pounds, which is the mass of 1 pound under normal standard gravity. But if you take a regular, something weighs 1 pound on Earth, if you take it to the moon, it will weigh 1/6 of a pound because gravity is 1/6 as strong on the moon. And in fact, the weight of an object will vary slightly depending on where it is on Earth. If you go to a higher altitude, you'll have less weight because you're further from the center of the Earth. Similarly, as you travel south, closer to the equator, you also end up having slightly weaker gravity. It varies by as much as like a percentage point between the pole. Well, no, it's not quite a percent, but maybe 0.5% between the pole and the equator. So it does vary. Mass is a fundamental quantity. It remains constant. Your weight will vary. The last of these units is time. Both systems use the same unit of time. That is the second. Time only goes forward. Why time only goes forward is not known. That's one of those very difficult questions that has not been answered. But time only seems to go forward. The second is the standard unit of time, both the metric and the British system. It was originally defined as, there are 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So the second was 1/886/400th of a solar day. The problem is that the solar day varies. The length of a solar day can change. In fact, the rotation of the Earth is steadily slowing down. So technically it's getting longer. Various things we do can change that, which is why every once in a while they have to add a leap second or subtract a leap second. So when they built the Three Gorges Dam in China, it changed the rotation of the Earth and changed the length of the day because so much water piled up, it changed the rotational properties of the Earth. So it is now based on the vibrations of a cesium-133 atom. Because all cesium-133 atoms are identical, they all have this hyperfine transition that oscillates at the same rate. You can excite it with radio waves and count the vibrations that come out and use those to measure time. So if you've heard of an atomic clock, that's what an atomic clock does. It has some cesium atoms that it excites this hyperfine transition and counts the oscillations. You basically send radio waves in, you get radio waves out. It oscillates at a very specific frequency and you count the oscillations. So it was originally, the second was originally defined as a fraction of the average solar day. It's called a second because the origin of that term is actually from, you have first and second. It actually comes from that because the minute was the first division, it's minutia, and then minutia secondum, which was your second small division, which is what became the second. That was originally used for angles, and then that was co-opted for time. So we'll be talking about it for angles later. We'll talk about arc seconds. But you can split a degree into minutes and seconds. A second of time is defined by the radiation frequency of a cesium-133 atom. You excite a cesium-133 atom and it oscillates. It sends out radio waves. I think these are radio waves. Oh yeah, that's at 9 megahertz. That's definitely. No, that's at 9 gigahertz, but it's still radio waves. And 1 second is 9,192,631,770 oscillations. They're basically just counting these vibrations to define what a second is. And this lets you measure very small oscillations. There are people trying to design clocks that measure with even faster natural oscillations for when they're trying to measure even tinier amounts of time, which is kind of nuts. So the metric system uses the acronym of MKS system for the 3 base units that all the other units are built off of. These are the meter, kilogram, and second. It's a decimal, a base 10 system, which makes all the unit conversions quite easy because all you have to do is move the decimal point. Because our number system is also a base 10 system. By having all your units be based off the same system as your number system, it makes it very easy to do unit conversions. This is a lot more convenient than the British system, which has a bunch of historic stuff and is kind of a mess because it's actually several different unit systems glommed together. Several historic unit systems glommed together. Which is why nothing seems quite consistent. It's administered by the Bureau International des Poids et Mesures, the BIPM in Paris, which is the International Bureau of Weights and Measures, translate that into English. And it is the International System of Units, or Système International in French, which is why it is abbreviated SI. So the general abbreviation for the metric system is the SI system. And it contains 7 base units. There are 7 base units. These are the fundamental units that are defined for the International System of Units. The 3 primary ones that we're going to talk about a lot are the meter, the kilogram, the meter for length, the kilogram for mass, and the second for time. Those are the most important because you can do most of motion and other things with those 3 units. So the unit for length is the meter, the unit for mass is the kilogram, the unit for time is the second. For electricity, the unit for electrical current is the ampere. The reason it is the ampere and not the unit for electrical charge is because it turns out it's a lot easier to measure current than it is to measure charge. So historically, the unit for current was what was defined. The unit for temperature is the Kelvin. 1 degree Kelvin is the same size as 1 degree Celsius. So there's 100 degrees Kelvin between the freezing point of water and the boiling point of water. But the Kelvin temperature scale, instead of starting at the freezing point of water, like the Celsius temperature scale does, starts at absolute zero, the coldest temperature that exists. And that's very convenient for scientific purposes, because starting at absolute zero means that your temperature value corresponds to the internal energy of the substances that's stored in heat and things like that. There's the mole, which is the amount of a substance. A mole is a thing that's like a dozen. It's just a number. It's 6.022 times 10 to the 23rd. It's a very big number. But the idea is that if you can use moles to convert to basically count large numbers of molecules or atoms by weight. So 1 mole of carbon-12 weighs exactly 12 grams. So it allows you to count how much of like an atom or a molecule you have based on the atomic mass of that atom or molecule and the mass that you weigh in grams. And it lets you go back and, basically lets you go back and forth between mass, which is easy to measure, and number of molecules, which is very hard to count. And then lastly, there is the candela, which is a measure of luminous intensity, how bright something is. Turns out candelas don't get used very often. The fact that it is a base 10 system is quite convenient. And so some examples, we go from 1 kilometer to meters. 1 kilometer is 1,000 meters. That's an easy conversion. You just move the decimal point 3 places. On the other hand, 1 mile is 5,280 feet, which is awful. It's actually extra unfortunate. It ended up particularly ugly because of some historical reasons. Like, for example, the Roman mile was exactly 5,000 feet, which is much nicer. 1 meter is 100 centimeters. 1 yard is 3 feet or 36 inches. Not as nice. A liter is 1,000 milliliters, while a quart is 32 ounces or 2 pints, and a gallon is 128 ounces. Not as nice. But those are all powers of 2. They're not that bad. So the way the metric system works, you have a base unit, and then you put a prefix on it. And the prefixes are the same for all units and can be applied to anything. And they're just, the prefixes are multipliers. If you have a capital M or mega as your prefix, that means 1,000,000. So a megagram is 1,000,000 grams. A megaliter is 1,000,000 liters. A megaton is 1,000,000 tons. A megabuck is $1,000,000. A megabyte, which is probably what you've encountered, is 1,000,000 bytes. The big units tend to get used for computing. So for the big units, a kilo is 1,000. That shows up a lot. Kilometer, kilogram, kilometer, kilogram, kiloton. Guess you could have a kiloliter, but no one ever talks about that. And then as you go bigger, there's mega, which is 1,000,000, giga, which is 1,000,000,000, which is a capital G, and tera, which is a trillion. Tera, which is a trillion. But there are also smaller ones. So if you want to deal with 100th of your base unit, that is centi. So you can have centimeter, centiliter. That is expressed with a lowercase c. Then 1,000th of your base unit is milli. So millimeter, milligram, millisecond. And that is milli, it is expressed with a lowercase m. So it's important to know the difference between lowercase m is milli, 1,000th, uppercase m is mega, 1 million. There's a full table on page 13 of your text. I will give, if you need to do conversions, I will be giving you conversion factors for units, between systems from imperial, from, US to metric or vice versa. But I will expect you to know what all the prefixes mean. There is a table on page 13 that extends this. If you want, I can pull up the whole table. There are prefixes for every 1,000 going up and down, and then there's prefixes for 10 and 100 going up and down as well. 10th and 100 up and down. But there is a complete table in your book on page 13. The liter is the volume of liquid in a 10 centimeter cube. It's 1,000 cubic centimeters. And a liter of pure water will have a mass of 1 kilogram or 1,000 grams. So 1 cubic centimeter of water has a mass of 1 gram. That means the density of water is 1 gram per cubic centimeter. This is incredibly useful and convenient. And by definition, 1 liter is 1,000 milliliters, because that's just what milli means. Milli is 1,000. So there are 1,000 milliliters in a liter. So 1 milliliter is a 1 cubic centimeter, which is 1 gram of pure water. So you may have seen a scale that weighs in milliliters. That's actually a setting on some scales, like kitchen scales. That is just weighing in grams, and assuming that the thing has a density equal to that of water. So 1 milliliter equals 1 cubic centimeter for all liquids. 1 milliliter is always 1 cubic centimeter, but not all liquids will have 1 cubic centimeter will have a mass of 1 gram. Water is 1 gram. Alcohol is less at like, I don't know, it's 0.9 or something. Mercury, on the other hand, weighs 13.5 grams for 1 cubic centimeter. So the density of various liquids varies. You measure that density, you can find things out about the liquid. A liter is a little bit more than a quart. You're almost certainly familiar with quantity of liters because we sell stuff in liters. You probably bought a 2-liter bottle of soda, or at least seen one. The liter is a little bit more than a quart. A 1 liter is 1.06 quarts, so 1 quart is 0.946 liters. And a kilogram is the mass of 1 liter of water. So 1 liter of water, the amount of water in a 0.1 meter cube, has a mass of 1 kilogram. Now, it's actually kind of tricky to make any measurements directly with just the fundamental units. So what we've done is we've derived units based on them that are combinations of these fundamental units. We've already talked about some. Volume, for example, is length cubed. So that's meters cubed, centimeters cubed. It's length cubed. Area is length squared. Square meters, square feet. Speed is length over time. So this will be things like meters per second, miles per hour, kilometers per hour. Now, something that we will talk about is density. Our first lab will be about density. Density, which is, the official symbol is rho, but we can also just use a capital D. and that is mass per unit volume. So you take the mass of something divided by its volume. It measures how compact something is. Typically, it is measured in grams per cubic centimeter or grams per milliliter. These are in fact the same unit because a cubic centimeter and a milliliter are the same size. Grams per cubic centimeter tends to get used for solids. Grams per milliliter tends to get used for liquids. Just because you tend to measure liquid volume in milliliters instead of cubic centimeters. Technically, the official unit with the standard units would be kilograms per cubic meter. It just turns out that that combination is awkward because the density of water is 1 gram per cubic centimeter. It's a nice reference. All these standard, like everyday things, like aluminum is 2.7 grams per cubic centimeter, iron is 7.8 grams per cubic centimeter, gold is 19.3 grams per cubic centimeter. These are nice, smallish numbers that people can deal with. In kilograms per cubic meter, aluminum is 2,700 kilograms per cubic meter. Iron is 7,800 kilograms per cubic meter. Turns out kilograms per cubic meter are just kind of awkward for everyday use. Also, the quantities involved most of the time are on the scale of grams and cubic centimeters. So, if I measure the volume of this, it's more convenient to measure it in centimeters, cubic centimeters, than in cubic meters, because a cubic meter is really big. And the weight, it's convenient to measure in grams. So the typical unit is grams per cubic centimeter. The average density of Earth is 5.5 grams per cubic centimeter. In general, the Earth gets more dense as you go closer to the center, as you move towards more metals, iron and nickel in the core and things like that. The average density of the crust at the surface is only like 2 or 3, is around 3 grams per cubic centimeter. Now, sometimes we need to go from one unit to another. For this, we use conversion factors. To convert from one unit to another, we need to know that how much one unit equals in the other. So for example, 1 inch is equivalent to 2.54 centimeters. So 1 inch equals 2.54 centimeters. That's our conversion factor. For things like between the metric and imperial system, I will give you the conversion factor on tests and quizzes. So if you want to know how many centimeters there are in 65 inches, well, 1 inch is 2.54 centimeters. So 1 inch divided by 2.54 centimeters equals 1. Or 2.54 centimeters divided by 1 inch equals 1. And if you multiply something by 1, it doesn't change. And that means we can always multiply by 1 and not change how much we're dealing with. So if we want to get rid of inches and end up with centimeters, we can take 65 inches and multiply by 2.54 centimeters divided by 1 inch. The inches will cancel, and we'll be left with centimeters. So 65 inches times 2.54 centimeters is 165 centimeters. The inches will cancel out. So in general, you're going to make a ratio. You're going to put the two things that are equal to each other on top of each other. So you're multiplying by 1. And generally, you're going to put the unit you're trying to get rid of on the bottom, so it will cancel out. So if you're trying to get rid of inches, you put inches on the bottom, so it cancels. There are some exceptions there. You try to do 1 over a unit, but that's the general rule of thumb. So the general idea is choose or use a conversion factor. You can generally look these up. There's a table of them in your book. I'll be giving them to you on tests and quizzes. You can figure them out from the metric prefixes if you're converting metric units. Then you can apply the conversion factor into the appropriate form so the unwanted units cancel out. So it's, if you're going from inches to centimeters or vice versa, you'll use either 1 inch over 2.54 centimeters or 2.54 centimeters over 1 inch. And then you can multiply or divide to calculate the answer. And use some common sense to anticipate what your answer. If you're going from a larger unit to a smaller unit, you should end up with more of the smaller unit. So if you were going from inches to centimeters, you should end up with a bigger number. If you're going from a smaller unit to a larger unit, you should end up with less. So if you were going from, I don't know, grams to ounces, you would end up with fewer ounces than grams. You can also do multiple step conversions. And you don't need to do complete one and do the next. You can just sort of line them up. So if you wanted to know what 18 inches was in meters, well, you know the conversion factor from inches to centimeters. That's 2.54 centimeters over 1 inch. And then you just need to convert from centimeters to meters. Well, 100 centimeters equals 1 meter. So we start with 18 inches. We multiply by 2.54 centimeters per 1 inch. We multiply by 1 meter over 100 centimeters. Inches cancel, centimeters cancel, and we're left with 0.46 meters. Here's another example. How would you express first and 10 in meters? Well, first and 10 is first and 10 yards. So what is 10 yards in meters? Well, 1 yard is 0.914 meters. It's a little bit less than 1 meter. So we start with 10 yards, and then we multiply by 0.914 meters divided by 1 yard, and get a result of 9.14 meters. So 10 yards times 0.914 meters per yard equals 9.14 meters. So let's go through a few examples of conversion. Top three here are all metric conversions. I've included the metric conversions up here. 1 centimeter is 1/100th of a meter. 1 kilometer is 1,000 meters. Centi is 100th. Kilo is 1,000. Milli, 1 millimeter, is 1,000th of a meter. Milli is 1,000. So we want to convert 15 centimeters to meters. So 15 centimeters. Oh, did I not? I could have sworn I worked these out. Oh, well, I'll just write about them. I'm sorry I didn't include the work done on the slides, but I'll just work this out. We have 15 centimeters. We know that 1 centimeter is 100th of a meter. So divided 100 centimeters to 1 meter. And so 15 divided by 100 is 0.15 meters. You can see, because we're just dividing by a power of 10, we just move the decimal place 2 places. Now here we have 25 meters to kilometers. We have 25 meters, and we'd like it to be in kilometers. Well, 1 kilometer is 1,000 meters. So we're dividing by 1,000. So we'll move the decimal place 3 places to the left. So it's 0.025 kilometers. Now here we have 250 millimeters, and we'd like to convert it to centimeters. But we don't know a direct conversion from millimeters to centimeters. You might know it, but we're going to assume that we don't know this. But we do know that that 1 centimeter is 1/100th of a meter and 1 millimeter is 1,000th of a millimeter. So we have 250 millimeters. First, we're going to convert to meters. So 1 meter is 1,000 millimeters. And then 100 centimeters is 1 meter. So millimeters will cancel, meters will cancel, and we'll be left with centimeters. So 250 divided by 1,000, that moves the decimal place 3 places to the left. Then multiplied by 100, which moves it 2 places to the right. Leaves us 1 place to the left at 25 centimeters. And then lastly, we need to convert 25.7 grams to ounces, given that 1 ounce is 28.35 grams. Well, we start with 25.7 grams. We want to get rid of grams, so we're going to put it at the bottom. That's 28.35 grams. And we have 1 ounce on top. And for this, you need a calculator. Now, where did I put my calculator? So 25.7 grams divided by, times 1 ounce divided by 28.35 grams. The grams cancel. And we get me failing a brain. 0.907 ounces. That's rounded off to 3 decimal places. 3 significant craters. That's the most accurate value. Any questions about conversion? So this is to which one is
Like just for all, like are we, like, you see where your 15 is, are we adding that to the, right?
These are multiplied. This is always multiplication. Multiplication and division. So we're multiplying 15 by 1 and then dividing by 100. This is 25 times 1 divided by 1,000. 250 times 1 times 100 divided by 1,000 times 1.
Didn't you also look at like, where, so like for these, 15 centimeters times 1 meter over 100 centimeters, right?
Yeah.
If you go like X over 15 centimeters times 1 over 100, because we know that 1 meter equals 1,000 centimeters. How many meters gives us 15 centimeters? That's kind of the way I look at it.
That's this. That's
yes.
That'll do the same thing. This is just sort of the ratio that you multiply by. This is more helpful if you're doing a bunch of them in a row, because you can always just add another ratio.
Right. Yeah.
To the end. So basically we're taking this thing and we're dividing one side by the other and getting 1 equals. For this particular class, you don't need to do a lot of these, but general idea is, yeah, this is all multiplication. Sorry, let me put in, I'm just so used to implied multiplication. Now another example you could do, I'll this is what, 15 centimeters times. You could also write it as 10 to the minus 2 meters over 1 centimeter. And then this is 15 times 10 to the minus 2, right? The general idea is that you're multiplying by a ratio where the top and bottom are equal to each other. So that's the same as multiplying by 1. So you're always going to multiply by the top and then divide by the bottom. Let's see. Okay with me erasing this? So when you make a measurement, there's always some error. No measurement can be perfect. So there's two ways we can describe the error of that measurement. So all measurements have an inherent error, the difference between the experimental and accepted values for the measurement, no matter how carefully the measure is made. And we can talk about the agreement between measurement and reality in two ways. There is accuracy and precision. Accuracy is the magnitude of agreement between experimental and accepted values of measurement. This is measured through percent error. This is how far you are off from the true value. So in an example, if you're shooting a gun at a target, accuracy is how well you hit the bullseye. Precision is the magnitude of agreement among several measurements taken in the same way. Precision is how tightly grouped your measurements are. And then what? Oh. So you can make measurements that are very precise, but not very accurate. So if you were firing bullets at this would be something that is very precise, but not very accurate. All of your shots are very close together, but you're missing your target. This would be something that's not very precise, but is very accurate. Your grouping is centered perfectly around the bullseye, but it varies a lot. And we express precision through significant figures and accuracy through percent error. So significant figures are a way when we're writing out a number to tell how precise that measurement was, and we want to preserve that information through calculations. So significant figures include all the digits in a measurement known with certainty, plus the last digit in that measurement that is estimated. So when you're measuring on a ruler, for example, the digits done with certainty are the marks on the ruler, and then you can estimate an extra digit in between the lines. Or if you're weighing with the scale, you might see that last digit wobbles a bit. That's that last digit of measurement. That is the end of the significant figures. So here we have two measurements that have an error. And we want to know which measurement situation demonstrates greater accuracy. We could have a rock sample that weighs 500 with an accepted mass of 500 grams, and we weigh it, and it has a mass of 499 grams on our scale. Versus a rock sample with an accepted mass of 2 grams, which when we weigh it, we get a mass of 1 gram on our scale. So which of these do you think is the more accurate measurement? The 499 one, yes. Because the error, they have the same size of error in number of grams. They're both off by 1 gram. But 1 gram is a much smaller portion of 500 grams than it is of 2 grams. So if you calculate the percent error is the measured value minus the accepted value divided by the accepted value, and then you multiply by 100 to make it a percent. So 499 grams minus 500 grams divided by 500 grams times 100 gives us negative 0.2%, while 1 gram minus 2 grams divided by 2 grams gives us negative 50%. That first measurement of the 500 gram mass, 500 gram rock, is the more accurate measurement because the percentage, the percent error is much smaller. You know, the error is a smaller portion of the whole. So that's accuracy. Accuracy is how well you're hitting the true value. This is often kind of hard to determine because you don't actually know what the true value is a lot of the time. So in fact, in our first lab that has a percent error thing, I'm going to have you not actually calculate it because I don't have known values. But we can talk about precision. So here are two measurements. One is 2 grams, the other is 2.000000000. I don't know how many zeros I just said. Grams. So there's two questions here. Are these 2 grams the same or different in magnitude? Are they the same or different in size? They are the same. They're both 2 grams. Which of them is the more precise measurement? Sorry. This is the more precise measurement. So here I'm saying, I know this to the nearest gram. It might be 3, it might be 1. Here I'm saying, I know this down to the 1, 2, 3, 4, 5, 6, 7, 8,
1
9,
million
10
of a gram.
More than 1 million.
1 billion of a gram.
I think it's
Or 10 million.
a 10 million on a gram.
And
It's absurd. I know this to some absurd precision. I know it to the nearest 10 billionth of a gram. You might go up or down by 1 10 billionth of a gram or something like that. That's not even a speck of dust. So, and I can tell this is more precise because it has more significant figures. This has 1 significant figure. This has 11. In both cases, all of the digits here are significant. There's 11 here and 2 over there. So we express this with significant figures. And if we use these numbers in calculations, we need to preserve the information about how precise our measurement was. Which means we need to round our answers so that we have the same number of significant figures in our output as we did in our input. And actually what we do is we use the worst of our input, the least number of significant figures in our input. So we have a little more time, so I'm just going to go over some stuff about significant figures. So significant figures are a method for expressing measured numbers to their correct level of precision in a mathematical operation, such as multiplication, division, addition, or subtraction. Cannot give you more significant figures than you start with. So, for example, 6.8 has 2 significant figures, 1.67 has 3 significant figures. These 2 and these 3. If we do math with these 2 numbers, we need to get out the same, we need to express the same number of limited precision that we had going in. If we multiply these together, for example, on a calculator, we get 11.356. But 6.8 only has 2 significant figures. I don't have 5 significant figures of precision here in my calculation. I only have 2, so I would need to round this off to 11. That's not a huge deal with multiplication. It becomes a much bigger deal when you divide. Because when you divide on a calculator, your calculator knows nothing about significant figures. It's not going to even try, which is very much the correct decision. So we'll tend to give you lots of digits. So if you type 6.8 divided by 1.67, you'll get 4.0718563. That is way more precision than our actual measurement had. So we need to round off to two significant figures. So we count from the beginning, we have 4. This is one significant figure, two significant figures. Then we can look at the next digit. That is greater, 5 or greater. So this is closer to the next number up. So we would round this to 4.1. So the general rule is report only as many significant figures in the result as there are in the quantity with the least significant figures. And when multiplying and dividing, express the answer to the same number of significant figures as the measurement with the least number of significant figures. So 6.8 centimeters divided by 1.67 centimeters, you round off 4.0718563 to 4.1. The limiting term is 6.8, which only has two significant figures. Now, technically, the rule for addition and subtraction is slightly different. For addition and subtraction, instead of significant figures, you actually use decimal places. Usually, significant figures and decimal places will give you the same answer. I'm not going to be picky. If you use either one, I will treat it as correct. I will accept both roundings. But the general rule is when adding and subtracting, express the answer to the same number of decimal places as the measurement that is expressed to the least number of decimal places. So here, 5.687 plus 11.11. The limiting number is 11.11 with only two decimal places. So you would round 16.797 up to 16.80. So if you use significant figures, both of these have 4 significant figures. So the limiting term would still be 11.11 with 4 significant figures, and it would still round to 16.80. So you get the same answer. Usually they come out the same, which is why I'm not very picky in this class. Because it's sort of a subtlety and it's not super important. So why do we care about significant figures? Because it tells us something about the measurements we made and how well we know things. So for example, if a rock sample's mass was determined in the field to be 45.666300 grams, using a very precise balance for no good reason at this point. When brought into the lab, the volume was determined through water displacement to be 6.5 milliliters. Problem here being the disparity between the way we're measuring values. So the density was determined to be 45.666300 grams divided by 6.5 milliliters, giving 7.0255841615 grams per milliliter. Would it be acceptable to record the density as this figure? Or if not, what should you be recording it as? So, do you think this is an acceptable way to record the density? Yes or no? No. This should be rounded down to the least number of significant figures in our input, which happens to be 2 from the 6.5. Yes, it would be 7.0. So 2 significant figures in 6.5 milliliters. So this would be rounded to 7.0 grams per milliliter. So this was rounded up to 16.8. This was also rounded up to 4.1. So the rules for significant figures. When you look at a number, all non-zero digits are significant. So both 23.4 and 234 have 3 significant figures. Zeros in between non-zero digits, zeros in the middle, are also significant. Your significant figures will always be a big block. So 20.05 has 4 significant figures, 407 has 3 significant figures. Zeros are not significant if they're on the front. Leading zeros used to locate a decimal point are never significant. So 0.000035 only has 2 significant figures. The leading zeros will never count. Zeros to the right of non-zero digits, trailing zeros, are significant if there is a decimal point. So 45.0 has 3 significant figures, but 4500 only has 2 significant figures, so this does not have a decimal point. Sometimes on tests, if I want to write a nice round number, but have it have more than just 1 significant figure, I will write something like 100 with a decimal point at the end. This would have 3 significant figures, because there is a decimal point. Don't think I do that on any of the tests in this class, more other classes. So here are some questions. How many significant figures does 200.0 grams have? Yes. How about 0.00458 grams? Yep. 0.00400 grams? Also 3, yes. And 505 grams? 3. How about 5 cupcakes? This is one of the exceptions. This is an exact number of things. We're not talking about we have 5.3 cupcakes or something. We have exactly 5 cupcakes. It's just a count. We know this to perfect precision. For exact numbers, like numbers of people, items, etc., they're assumed to have an unlimited number of significant figures, and we don't have to include them in a problem. So for example, if a typical cupcake has a mass of 85 grams, what's the mass in grams of 8 cupcakes? Here we can ignore the number of significant figures in that exact count of cupcakes. And we just multiply 85 grams by 8 cupcakes and get 680 grams. And we would round it to 2 significant figures. And in the process of determining the number of significant figures, you generally also round off numbers. So the first digit, if the first digit to be dropped is less than 5, we leave the preceding digit unchanged. If the first digit to be dropped is 5 or greater, we increase the preceding digit by 1. And I will go over this again on Tuesday. So that is all for today. Have a nice day. Remember, you have an SI class today at 11:30. It is in room 268. Yeah. So